and welcome to the presentation of the WU paper, a linear time parameterized algorithm for computing the width of a DAG. My name is Manuel Cáceres, and this is a joint work with Massimo Cairo, Brendan Mumey, Romeo Rizzi, and Alexandru Tomescu. First, let me introduce some notation. We will be working with directed acyclic graphs or DAGs, which are directed graphs that don't contain directed cycles. In a DAG, we can compute a topological ordering in linear time in the size of the graph. A topological ordering is a total order of the vertices such that the edges of the DAG go in the same direction as in this order. We will be using the topological induced subgraph GI, which, given a topological ordering of the vertices, is just the induced subgraph by a prefix of this topological ordering. We say that U reaches B if there is a path in the graph from U to B. We also say that we have constant time reachability queries if we have a data structure that answers these queries in constant time. An antichain is a set of vertices of the DAG that are pairwise non-reachable, that is, there are no paths between them. We say that an antichain reaches a vertex B if some of the vertices of the antichain reaches this vertex. A maximum antichain is an antichain of maximum size among all antichains of the graph. The width of the DAG is defined as the size of a maximum antichain. We denote it by k, in this case 4, and it is the parameter we are interested on. Some applications of computing the width of the DAG are in bioinformatics, where, for example, the problem of perfect phylogeny haplotyping is solved by recognizing DAGs of width at most 2. In evolutionary computation, the so-called dimension of a game is computed by computing the width of a DAG formed by the game. In distributed computation, this problem solves a generalization of the mutual exclusion violation. But why parameterized by k? First, because it is a natural parameter, it is the size of the solution. Second, because there are applications that have a small width. For example, in bioinformatics, a pangenome is a graph representing a genomic sequence and variations of this. These graphs are usually long, but they are thin, that is, they have a small width. Finally, another reason is that there exists fixed parameter tractable algorithm for hard problems parameterized by the width of the DAG. Some of these applications can be found in scheduling and computational logic. All but one state-of-the-art algorithm for computing the width are based on minimum path cover. A path cover of the graph is a set of paths that cover all the vertices, that is, every vertex belongs to some path in this collection. And a minimum path cover is one of minimum size. Dilworth's theorem states that the size of a minimum path cover is equal to the size of a maximum antichain of the DAG. As such, we can compute the width by computing first a minimum path cover of the graph. Minimum path cover algorithms are divided into those in a reduction to maximum matching, which can be solved by just applying the Hopcroft algorithm, but that this only works for poset or transitive DAGs. More developments on this idea obtain other parameterized solutions by K. Other set of solutions are based on a reduction to minimum flow of the problem. The most simple solution reaches complexity order b times e, and a recent improvement of this obtains complexity order k times e times log b. It is worth mentioning the work of Felsner et al. Recognizing poset of bounded width. They show how to recognize poset of width at most 3 in linear time, and of width 4 in linear-rhythmic time. But they state that their combinatorial approach seems to require an unpleasantly involved case analysis for the case k equals 5 onwards. Our result is a linear time parameterized algorithm for computing a maximum antichain, and therefore the width of the DAG. We say that an antichain B dominates an antichain A if they are of the same size and every vertex of B is reached by A. This definition, this relation between antichains, is pretty similar to what Dilworth used to show that the set of maximum antichains is a DAG form a distributive lattice, but this is a different definition. We show that domination is a partial order on the antichains of D. As such, we can define the maximal elements of this domination relation as frontier antichains. In other words, frontier antichains are antichains that only are dominated by themselves. We prove that the number of frontier antichains is bounded by a function of k. In particular, there are no more than 2 to the k frontier antichains in a DAG. If A is a frontier antichain of D, we also say that A is G frontier. We classify GI frontiers into 2 categories: the ones containing vertex BI and the ones who don't. For the ones containing vertex BI, we call them type 1. If A is a type 1 GI frontier, then if we remove this vertex, we obtain a GI-1 frontier. Moreover, if B is a GI-1 and B doesn't reach BI, then the union of B and BI is a type 1 GI frontier. For the type 2 frontier antichains, they are GI-1 frontier also. Moreover, if B is a GI-1 frontier but not GI frontier, then B is dominated by a type 1 GI frontier. These 4 lemmas about frontier antichains give us a way to compute them. For example, type 1 frontier antichains can be obtained from GI-1 frontier antichains and checking reachability to the new vertex BI. On the other hand, type 2 frontier antichains can be checked by check domination between type 1 GI frontiers and GI-1 frontiers. We put this into a simple algorithm that works posets for only 4 posets and is a simplified version of our final solution. In our algorithm, we process the vertices in a topological ordering and consider the corresponding topologically induced subgraph. At each step, at each iteration, we compute the GI frontier antichains. We first compute the type 1 frontier antichains, and then we compute the type 2 frontier antichains. When we finish processing, we report the largest frontier antichain seen during the algorithm, which corresponds to a maximum antichain. This approach takes order k squared 4 to the k times b if we assume constant time reachability queries or if we are working with posets of transitive DAGs. To obtain a solution for general DAGs, we need to maintain constant time reachability queries among the vertices. However, we observe that when computing GI frontiers, we only need reachability among vertices of GI-1 frontier and BI. We define the support SI as the vertices in GI frontier antichains. In this example, S10 contains all the vertices that are in some G sub 10 frontiers antichain. We prove that as we process the vertices in topological ordering, a vertex Vi enters the support Si and then abandons some later support. But it belongs to all supports between these two supports. This structural movement of vertices among supports imply theorems 2 and theorems 3 of our paper. We can reformulate our observation based on supports, as when computing GI frontiers, you only need to maintain reachability among vertices of the support of I-1 union Vi. We reduce this problem to maintain reachability from vertices in S sub j-1 to Bj for each j less than or equal than I, which is theorem 2. We then show how to maintain reachability from Si-1 to Vi in an inductively manner, and only paying order k times 2 to the k per edge incoming to Vi, which is theorem 3. Using these theorems and our previous algorithm, we obtain an algorithm for computing the width of a DAG in time ordering k squared for 2 to the k times b plus k to the k times e, which is a linear time parameterized algorithm for the problem. I'd like to finish by thanking the anonymous reviewers for their useful suggestions to improve our work, and you for listening until the end of this presentation. Thank you.